Hello again, physics friends. Today we are going to do a sample problem dealing with potential energy functions in one dimension and how they relate to stable equilibria and Hooke's law. So I pulled this question out of Taylor, and let's just get through it, right? So here we're given a potential energy that's a function of one variable, r, which is the separation, in this case, between two atoms. So here we're representing the interaction potential between atoms in a molecule using the so-called Morse potential. We're told A, R, and big R and S are positive constants, and S is much less than R. So first we're asked to sketch this function over the interval r is 0 to infinity, and we want to find any equilibrium separations at which the potential is a minimum, so that indicates we're going to look at derivatives of the potential. And then we're asked to expand this function in R about the minimum such that x is a little displacement from that equilibrium position, and show that in that vicinity of equilibrium, the potential is approximately a parabola. Okay? And if the potential is approximately a parabola, that is the potential of a spring, so Hooke's law should apply near that equilibrium. And what is the corresponding spring constant K? So let's start in the beginning. We want to draw this potential, right? So yes, you could go online and just draw it, or use a calculator to draw it, but there's benefit in understanding the potential by exploring different regimes of this potential. So let's just think about different scenarios, different values of R, and what the value of the potential is for those values of R. So one starting point might be, well, what if I turn off this exponential? I turn off that exponential by setting little r to big R such that I have e to the 0. So let's look at the case where little r is equal to big R. And in that case, my potential at that point, capital R, is a times the quantity e to the 0 minus 1 squared, all minus 1. E to the 0 is 1, 1 minus 1 is 0, so I end up with the potential being negative a at that point. So now I know that my potential goes negative at some places. Okay. What other regimes can I think about? Well, how about when R approaches infinity? So for very large separations. And we expect that if you take these two atoms in the molecule and separate them by a large amount, that the force would go to 0. So we expect the potential to be very flat, because you recall that the force is given by the derivative of the potential with a minus sign. So if the force goes to 0 when the atoms are very far apart, the potential must be very flat. And so we expect the potential to be very flat for a large separation. Let's see, what happens when r goes to infinity? When r goes to infinity, we'll have e to the minus infinity subtracted off of 1. So we'll have u of r is approximately a e to the minus infinity minus 1 squared, like that. So this term would be 0. 0 minus 1 is minus 1. Minus 1 squared is plus 1. So this whole term is 1. Minus 1 gives me 0. So the potential approaches 0 as r approaches infinity. Okay, and we know that there's a point at r equals capital R where the potential is negative and equal to minus a. And we expect that the potential will be flat at infinity, pretty flat. So it looks like this potential is approaching 0 from below. Perhaps this is our local minimum at a capital R, but we haven't determined that yet. So it'd be nice to know what happens near the origin. Okay, so near the origin, we have, or let's just take it at the origin, we have a times e to the capital R over capital S minus 1 squared. And recall, we're told that big R is much bigger than big S. And so this term is huge. It's e to the large, which is a big number in and of itself, so we can ignore the minus 1. And so this ends up being a times e to the 2r over s minus 1, but we can ignore that minus 1 also. And this number is huge because r is much bigger than s. So as you approach the origin, the potential gets huge. As you get far from the origin, the potential gets very flat. And maybe this is our minimum, but let's verify. It turns out it is, but let's show that that is indeed the case. So let's look for minima or maxima. Okay, so for that, we're going to take a derivative of the function with respect to r and set it to 0. The derivative of this function looks like the following. We have 2 e to the r minus r over s minus 1 to the first power times the derivative of what's inside. That's a 1 over s with a minus sign, like so. And the minus 1 goes away. Okay. In order for this term to be 0, we need this term to be 0. That's the only way we're going to get 0 here. So that tells us immediately that e to the capital R minus r over s minus 1 has to be 0, which means this exponential term has to be 1, which happens when the exponent is 0, which happens when little r is capital R. So that is, in fact, our minimum right here. And so we can kind of sketch in the rest by eye. We're just approximating the graph, like so. And there we have our potential. And in fact, I'm going to label this little r naught, because by that we mean the position of stable equilibrium. And in fact, that is what this is. So if we look at this potential, the claim is that any minimum in a potential, near any minimum in the potential, it behaves like a mass on a spring. So what that means is there's some parabola that approximates the actual potential near the minimum, and we want to study this parabola. That's like 1/2 kx squared, where x is the departure from r naught. In other words, the position r is equal to r naught plus this little x. And so we want to know, what is this k? How stiff, in quotes, is that spring that's approximately quantifying our potential near the equilibrium position? So let's find out. So how do we make this approximation? Well, we're going to use this statement that near the equilibrium, we're going to write, we'd like to express our potential in terms of x, where x is the displacement from the equilibrium. And remember that equilibrium is capital R, where R equals capital R. So we're going to use this x variable to represent our displacement from our minimum of our potential. And so our goal is to take this potential u of r and express it instead in terms of a potential with respect to x. And that potential with respect to x is what's going to give us the purple parabola that we drew already. Okay, so how do we actually make this expansion? Well, we look in our function and we see what depends on r. It's just this exponential term. So our goal now is to rewrite this exponential term, e to the capital R minus r over s. We want to write that in terms of x. Well, capital R minus r is simply minus x. So we have e to the minus x over s, where x is the displacement from equilibrium. And we want to expand this in a Taylor series. Okay, and we want to end up with, we want to keep all terms that are of order x squared or less, like x to the first power, x squared, but we don't need to keep track of x cubed or x to the fourth. notice that our exponential is embedded in a parentheses that are squared. So when we do the expansion of the exponential, we actually only need to keep terms that are of order x to the first power, so that when we square those terms, our potential keeps all the terms that are of x squared or less. So we want to keep all terms x squared or less in the potential. So the implication is that we only need the linear terms in the expansion of the exponential. Okay. So how do we write the Taylor series to expand this exponential? Okay. Well, you'll recall a Taylor expansion looks at the following. It evaluates the function at the point of interest. Our point of interest is x equals 0. Adds to that the derivative of that function evaluated at the point of interest, and multiplies that by the displacement from equilibrium, that's x. And you repeat this process for all of the derivatives. You end up with this infinite series, but we are only going to need to keep the terms that are linear in x, so that when we square the exponential, the potential will contain all terms that are quadratic in x. So we really need to evaluate just the first derivative of this function. Okay. So the first derivative of our function with respect to x is going to be minus 1 over s times e to the minus x over s. And when we evaluate that at x equals 0, we get minus 1 over s, period, full stop. Okay. So our Taylor expansion then we can write as f at x equals 0 minus plus df dx at x equals 0, which is minus 1 over s times x plus higher order terms, which we don't need to keep. The function evaluated at 0 is 1. Right? We have e to the 0 is 1 minus x over s plus higher order terms. So what we have left now is that we want to return to our potential, u of r, and we want to re-express it in terms of the deviation from equilibrium. So we'll do the following. And our goal is to re-express that potential in terms of x, where x is a coordinate relative to r naught, relative to our equilibrium position. And we're going to do that by expanding the exponential. And we see that the expansion of the exponential gives us a 1 minus x over s, which we're then subtracting a 1 off of and squaring. So the minus 1's in the parentheses will cancel. We're squaring minus x over s, so that gives us plus x squared, over s squared. We still have that minus 1 out front. So this ends up being minus a plus a x squared over s squared. And remember, our goal is to write this as u of x equals some constant plus 1/2 kx squared, where k is our effective spring constant of this parabola. Okay, so we're very close. We have the constant, and we just need to rewrite this by being explicit about the 1/2. So if we're going to put in a 1/2, we have to put in a 2 up top in the parentheses, and now we have a potential that meets our goals. And we've identified what k effective is. The effective spring constant of the potential is 2a over s squared. So let's think about this a little bit, right? We have a potential that's not a parabola, but what we've just found is by expanding the potential near the vicinity of this local minimum, we get an expression that is very much a parabola that's shifted downward by a units. And you can see here, graphically, we have a parabola that's shifted downwards by minus a. Okay. So what is this saying? Remember, this potential is talking about the interaction between atoms in a molecule, and this r parameter is how far apart the molecules are. So what this is saying is near this equilibrium position, the atoms will be a certain distance apart, and that distance will be capital R. And that's kind of the equilibrium position. If you perturb the system a little bit such that the separation grows a little bit, then the system will oscillate about this equilibrium position, capital R. And what that means is these two atoms will move such that their separation grows and shrinks and grows and shrinks exactly in the same way that two masses would move on a spring. Okay? And that spring in this problem has a stiffness, and that stiffness would be given by 2a over s squared. Now, if you perturb this system too much, in other words, if you took one of the atoms and pulled it way to the right, well, now the system would not respond like it was a mass on a spring, because we're outside of the realm of validity for the parabolic assumption. We're over here somewhere. But near this equilibrium position, we can treat the potential as if it were a parabola, which is effectively having masses on a spring. So the separation between the atoms will just oscillate back and forth around capital R. So hopefully this problem has given you a sense of how to take a potential that is not a parabola, find a minimum, expand a potential mathematically about that minimum to show that you have a parabolic potential, and the coefficient of that parabolic potential, the k and the 1/2 kx squared, tells you about the effective spring stiffness of the system near equilibrium. So that's all we have for now, but until next time, take care and be well.